Hi, in this video, we want to take a look at further methods for handling spatial data. All right, so what we're talking about in this one really is more akin to like set theory than handling data. So we're going to be interested in taking a look at things like the union of different spatial data items or the intersection of spatial, spatial data. Ways to check to see is there an overlap, ways to check to see if there's a hole, things like that. All right, so this code is modified from the website for applied spatial data analysis with R. Here is the website where I got this from. The textbook can be downloaded for free through UCS library. So if you're a student, you can go get it easy peasy lemon squeezy. All right, so I'm copy and pasting to a large extent this code from the author's website. And the author says that we need these data sets to be able to run this code. Now, there's some other data sets that are needed that are in R that the packages have that we just need to use the data function to pull up. All right. And I've modified the code so that things just go along with how I like to do my naming conventions and how I like to use keywords and things like that. Okay, so the first thing to talk about is support. So when you hear support, really that's referring to the area that is under consideration with our spatial data. So in a sense, it's kind of like support in like market basket analysis support. What we have supporting our model data-wise. All right, so here's an example. Let's look at topographic information on Auckland's Mangawahu volcano. Okay, so it's one of 50 volcanoes in Auckland's volcanic field, and this data can be loaded from base R's datasets package. So I just go through, I load the data. It's already available in R, and here I'm using the str, the structure function, to take a look at what I've got, so I know what's there. And we can see that we have. This looks like, we can think of this as a matrix with 87 rows, 61 columns. Now, something about this is that the author multiplies all of the X and Y values by 10 and to get us a grid. So this indicates how far apart the grid points are. Then the author sets up the terrain colors, which is a base R function, and then goes through and builds up the image. All right, so what we have our, now something that's interesting to pay attention, if you look at the author's code, what is called Y is X, what's called X is Y, by what the author put in, because the author put in Y first, then X. And so I just labeled it the way, the author didn't use keywords. I put that in there. And then here, the Z, you'll notice that there's a transpose going on. And then there's a reversal of the column order. And then the breaks are the sequence from 90 to 200 by 10. Then we're coloring it by the terrain colors we had, and we're putting it on aspect ratio 1. Remember, that's always important. All right, so what will happen when I'm plotting something with default statistics plotting, it's always going to try and take up the entire space so that we can get like a better view of the data. That's the base, the base statistics way of plotting. When I'm doing something with spatial data, I don't want that because I need to keep that ratio correct. Otherwise, we could have like the state of Florida looking like really, really, really wide. And this is just saying don't put the axes on. So let's take a look at what we get. Okay, so something that is important for what's going to happen in a moment. Look at how granular this looks. You notice how everything, we see all these right angles and straight lines. Do you think the actual elevation goes like that? Looks like stair steps? No. Pretty sure that's not what's really going on. So the point of this visualization is to demonstrate that we only have like a certain level of granularity in our data. We can only know so much about it. Now, let's look down here. What I'm going to do next is, I don't want to show the punchline. I'm going to take contour function in base R once again, my X and my Y, transpose, level is the same, aspect ratio, axes, everything's the same, except instead of image, and with colors, I'm using a contour plot. Now, let's take a look at what we got. Doesn't this look a lot smoother? Don't these lines look pretty smooth for like the boundary between elevations? So, you know, what this is saying is that every point along this line is at 110 meters above sea level. Every point along this line is 130 meters above sea level, and so on. And we have the corresponding information. If we were to take the colors and connect back to elevation, we have the same information in the previous slide or the previous image. Now, they're the same data. Okay, so what's going on here? This is actually what we have. This is truly what we have for our data. This is our best information that's going on. But when I pass it to this algorithm, you can see that it went through and made it look a lot smoother than the original data has. And so this, you know, intuitively, this looks a lot more like what I would expect to see on the ground. But, you know, there's a gap between the ground and my data and my map. And so by kind of filling in things, making it smooth, I get the impression that I have more precise information than I really have. Here, it's very clear, like, you know, how coarse my data is when I look at it this way. But here, it feels like I have much more precision what's going on. So this is something to be mindful of as we do our visualizations, as we reach our conclusions, is that just because it looks really good doesn't mean it's better than what you really have. All right, so now let's start taking a look at handling and combining features. And we're going to look at the RGeos package. So this is, you know, in R, handling like geometric, geographic operations. So geometric operations on geographic data. All right, so this paragraph is out of spot, but the get scale and set scales function are used to get and set the scale options in the RGeos environments. So this is used to determine the precision of the coordinates when translating to and from you know, objects in this package. So precision is defined as 1 over scale. So remember, in statistics, usually we'll say precision is 1 over standard deviation or 1 over variance, depending on which textbook, which author you're talking about. So here, let's go ahead and get scale. So this is going to be the default scale in R. And so we can see that it's 1 times 10 to the power of 8. Now, this part of the code is what the author put in, that this is an option to set do poly check. So here I'm saying don't do polynomial checks on this. And let's see. So this paragraph, the internal geos representation defines a polygon object as a collection of only one exterior ring and from 0 to many interior rings. So an SP polynomials object corresponds to a geo's multi-polynomial object. So this is important as we go back and forth between different object structures in R, but without proper hole assignments. And the default for do poly check is true. If we set it to false, polygon objects is not valid in geo terms. And so good warning, geos may crash R, which is why checks are imposed by default. So that's something to be mindful of. So if you're going to be working with the RGeos package, basically this is just saying, this is from the help documentation, by the way. Make sure that you're just saving your work as you go. I'm not familiar with this, the test that package, test package RGeos. I did not find anything on here. It was in the author's code. And here I'm setting the do poly check back to true. All right, so now let's start getting into using RGeos. And here we can use the set repels coordinates warn to turn off warnings. Just because, you know, as you work through this, you keep on getting all these warnings that get kind of annoying. We can turn it off if we just set it to false like we do here. All right, so now let's actually start working on an example. What we're going to do, we're going to take several spatial data sets for a city in Brazil. This is a historic city. You can look it up on Wikipedia or Google Maps. That's what I did before making the video. And it looks like an interesting place to go. I'm not going there in this video though. But we're going to take information about Olinda, Brazil, and we're going to be taking multiple spatial data sets and working with them in different manners. All right, so first and foremost, let's go ahead and load the shape file for Olinda, Brazil. And I'm going to go ahead and call this as Spatial Polygons Data Frame Olinda 1. The reason why I name it this is because the object is a spatial polygons data frame. So I have spatial polygons connected to a data frame. Here's the layer that I'm taking from the shape file. And I'm going to go ahead and allow a loss. And that's just so that we can process things. So we need some flexibility in making sure that different files will work together. So I'm allowing a loss. All right, and we get a warning about unknown projection definition. And we can see that we have 470 features and 6 fields. All right, so now let's go ahead and set our projection, or actually let's set our coordinate system, is a better way to say it. And we're going to go EPSG 467. And according to the author, this is a good one for that region of the world. All right, so now let's just do a quick plot, see what's going on. So I'm going to use the spplot function in the sp package, since it's a spatial polygons data frame. And we can see, boom, remember I had 6 fields, and we can see that those fields are like code, geo, code B, M Blair, Bear, V014 ID, a different code geo, code I, and then TIPO. My dog is trying to get in. All right, so now let's actually go ahead and switch to a better projection. So what we're going to do is this is one that the author said that is actually a better one to work with. It's very common for this area of the world to use. And here's the information that I've got. So this, remember, the make EPSG, this function gives us information about different projections that we have available to us in the RGDOL package. And so I looked it up beforehand. I found that it was row 3177. So I went ahead and just grabbed it. There's no row name, so you just use the row number. And here's its information. Here's its code. Here's its note. So you notice it's UTM, zone 25S. Here's its projection information, and it's transverse Mercator. All right. So now what I'm going to do, I'm going to transform what I had into this projection. So what was going on is that the data was originally saved with the previous projection. Now I'm using SP transform to get a better projection for the work that we are doing. And notice that to do this, I'm just specifying the code with this information here. So I'm just putting 31985 here. And let's go ahead and just plot it again, see what happens, see what looks different. So let's take a quick look. And to my eyes, I don't see much of a difference. It honestly probably wouldn't make much of a difference if we proceeded with, as is, but yeah, we'll keep going. And now I'm going to return the warning setting to true. All right, so now let's look at the area of geometry. So now what we want to do, we want to calculate the area of different geometric polygons. And so to do that, we're going to use the G area function in RGOs. So here, I take my spatial polygons data frame, and what is going to happen here is it's going to go through all of the polygons and compute the area. And so there's a bunch of them. Remember, there are, let's see, how many? Let's look back up. There are 470 polygons, and that could be, those polygons could be broken up in something like islands or broken up districts. But there's 470 of them. So rather than looking at 470 numbers, I went ahead and just put it in a histogram. And so the thing that jumps out at me very strongly is that clearly this is a skew right distribution. We have a few that have a lot, a large area compared to the rest, and then the vast majority are in this range here. All right, so now what I want to do, I want to get the area, and I want to store that on my data frame. So what we're going to do, I'm going to use the slot function. So I'm going to grab the slot for each of the polygons. So I'm grabbing this object, and I'm saying go to the polygons slot of the object, grab that. Now, once I get the polygon, each polygon has information about it. I'm saying grab the area of that using the slots. And now what I'm going to do, I'm going to check to see, is that the same as the G area calculation? Let's find out. All right, so what is going on is that my spatial polygons data frame had the area already for us. I could have just gone ahead and grabbed it, or I have the option of computing it. Well, if I had a data set that didn't have it computed for me, I would need that G area function. So just to see, is everything kosher? Is everything looking good? We're going to check to see, are these actually the same? So I'm going to take my G area calculations, and I'm going to compare it to the areas that I got from the polygons that are stored in the spatial polygons data frame. And yes, we can see with the all equal function that they're all equal. So it's good. There's an agreement. All right, so here, the author didn't say what this calculation is. I think it's population density because this data set corresponds to census data. So what we're doing here is I'm taking this number, which I believe is the population number. I don't actually know, I'm making a guess. Then I'm dividing by the area, and then I believe that this is rescaling for this being in a million people. 2 million. Yep. And so let's see what happens. All right, so we can see that we can get, a histogram looking at the population density of each of our polygons. So something that is interesting is how we have a few that are skew right for polygon size, and we have a smaller number are skew right for population density. So we definitely do not have like an even population distribution. All right, so now let's go ahead and now I've got this, let's look at the quantile for population density. So I'm going here, and the author chose to go from 0 to 1 in steps of 20. And so here's the lowest, here's the highest population density, and we can see that the middle is in this region. All right. So now let's go ahead and plot the population density of Olinda. So I'm taking my spatial polygons data frame. I'm going to say that the density, population density, is my Z. And then I'm going to chop things up there. Here, I'm going to define the colors I'm going to use. So we're going to have 1, 2, 3, 4, 5 bins. You notice that 6. Drop in the first one, there's going to be 5 different colors. We're going to throw in some gray in there also for a boundary. Here's our line width, and then we're keeping our color key. So here we go. And so here we go. We can see where we have a larger population density pretty easily. So this is kind of interesting. Like, there's not very many